Okay. We were at the notation. Yeah, this is very simple. Just how you can write derivative multiple ways, to be honest. These are different ways of writing derivative. If you have a function, it's y, right? Regular function, then y prime, f of x, then f prime, and this technically the same meaning. Okay, df over dx. Why this? But why? Okay, you know this derivative, right? That's derivative. But this notation also derivative. But why? Why you have that letter d, and then y dx over here?
Is it like a small change? Y divided by a small change in x.
Yes. Remember the true root of the derivative. Correct? Yes, you were correct. The true root of derivative is the limit of different quotient, right? Derivative is the limit of different quotient, right? Inside that different quotient, how did you get the different quotient? F of a plus h minus f of a divided by h, right? That came from the slope, right? They came from the slope of a tangent line, right? Slope we rise over run. The difference in term of y divided by the difference in term of x. Correct? That one, right? That's slope. That basically, when he say, well, what's your name? Ethan. When Ethan say that, that's technically the difference. Difference is the change, right? The difference. They usually call delta y over delta x. Del d delta. Instead of this is a Rick ladder. It's not a triangle. It's actually a Rick ladder. In Rick, that is a capital. Even in Rick, they have capital and lowercase letter. In Rick ladder, delta, the small delta is this. I hope you understand that. The capital delta is this triangle. That's actually Rick ladder. Okay, not triangle y, triangle x. You see this often, right? You say delta, it actually read out delta. That's a capital delta. That's why, and then in English, we use the letter D. Right? Okay, and delta usually actually in Rick convert to English, technically the difference. D, okay, the difference in y direction, the difference in x direction. Hence, we have this notation. Okay, and we're going to use this a lot in upcoming sections. We're gonna recall this notation to do implicit differentiation. Okay. All right. So just a little bit theory to warm up. Now, next section, differential function. Okay. This section we're gonna discuss when a function is differentiable. When can you take the derivative of a function? When I put the word when, that means not every function is differentiable. Not every function you can take derivative. Not every function. Actually, I can bring up a function that you cannot take. A function that you cannot take derivative. Oh, right here. Actually, right here. Oh my God. Right here. This function is not differentiable. We're going to actually analyze it. Why is not differentiable? Just give you the result first. This absolute value, you cannot take derivative at one point. Okay, at one point that is 0. Okay, but first, the really big important fact is that not every function is differentiable. Okay, in fact, there's a lot of functions not differentiable. Okay. For example, recall that the derivative is finding rate of change, right? The behavior of a function at a point on the curve or at everywhere. Okay. If the behavior at that point is irregular, okay, what does it mean irregular? The behavior irregular. It means it's undefined, jumping, a sharp, which is this one, this case right here. That is a sharp case. Or approaching infinity, yeah, then you cannot find derivative. You cannot take derivative now. Okay. All right, let's do this example. Absolute value. V for victory, right there. Right, absolute value. 0 at the origin. Okay. Okay, let's analyze differentiability everywhere of that function across the domain. So technically, this function, usually we analyze absolute value. We're going to analyze less than 0, right, on the left of 0 and on the right of 0. So less than 0, we technically we analyze this, right? When x less than 0, then we're going to analyze one more time when x maybe greater than 0. Okay. When x less than 0, absolute value of x equal less than 0. Negative x, right? This is the negative x. This is positive x, right? So negative. If you know for sure x is a negative number, then absolute value of x is negative x. Okay. We want to take derivative. F prime of x is going to be okay. This I hope from last week. If anything that you forgot, this one thing you shouldn't forget: the limit definition of derivative. Okay. 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 I split that into two. Okay. H on the bottom, everything the same. How about these two? Okay. F of x is this, right? F of x is that. But we'll consider the case when on the left. So on the left of 0, absolute value. Oh, actually, I should put the negative here too. On the left of 0. To be more specific, on the left of 0. Okay. Left of 0. The function f of x is negative x, so negative x right there. Negative x, and then there's a minus right here. This minus and this minus will be positive x. Okay. How about f of x plus h? Again, on the left side, you're going to have negative x, negative h. Right. Negative x, negative h. Less than 0. So anything inside, what does it mean? When it's less than 0, when you're analyzing on the left of 0, anything inside the absolute value, put the negative in the front. Okay, put the negative in front. Cancel. No, it's very easy, right? This one. Cancel. Negative h over h. Negative 1. Limit of negative 1. Limit of a constant is a constant. Just negative 1. Okay. Cancel a bunch of them. Okay. Do it one more time. This time, the positive side is very simple. You open the absolute value, you don't change anything. Right? Because this time is x greater than 0. Okay. So x plus h minus x cancel again. You have 1, positive 1. Okay. So on the right side, I maybe use a different color. Yellow here. You have this. Approaching 0 from the right, you have that. Approaching 0 from the left, you have negative 1. Okay. Look at these two limits. Limits approaching 0 from the left, negative 1. Approaching 0 from the right, positive 1. What will be the limit at 0? In other words, and then the limit at 0, from both sides 0. There's a derivative at 0, right? From both sides. Limit. This is limit at exactly 0. So I plug in 0. What will be your answer? I don't need to calculate this, right? D and E, right? Left side, right side, left side, right side. I don't need to calculate this. I don't need to plug in anything. At 0, it's D and E. And that limit is the derivative. The derivative at 0, D and E. Therefore, is not differentiable. There you go. Okay. In other words, okay, when you draw it out, the moment you draw it out, you already notice that. Okay. Here's a hint how you can tell a function that is differentiable or not differentiable. Okay. That means you can take derivative or not take a derivative. Okay. First thing first, that point right there. A function, first, in order to be able to take derivative, they had to satisfy two conditions. First, continuous. Continuous. So smooth, no jumping, no continuous. That means this. This is not discontinuous, right? Definitely, that's not differentiable right there. That's one thing. Second is, let's say, what's that? Asymptote, right? And then the function go down to negative infinity. Not differentiable right here too. Let's say pick a number 5, pick a number 3 there. Not differentiable at 3, not differentiable at 5. Another option, let's pick negative 2. Now you learn a new one right there. If continuous is enough, continuous is good, definitely that's continuous. F of negative 2, f of negative 2, let me give you the number, maybe 5. F of negative 2 equal 5, clearly. Continuous is 5 or not? Yes, continuous. But that's only the first condition. So far we learned that condition. If it doesn't satisfy the continuous condition, it's not differentiable. Good. Now the second condition, today we learn. It had to be smooth. Okay, that is very kind of vague, but it's still usable term in calculus. It had to be smooth. Smooth, that means this. Smooth, that means that. You cannot have an abrupt or sudden change of function. If you change like this, or pointy or sharp, those points, even though it's continuous, but it's not smooth, then it's not differentiable. Okay. That is what happened at 0 right there. Okay. Compare this to function. Give me something that look almost the same. Like that. Give me something. Another function that look very similar to that. But this time it's differentiable. But look very similar to that absolute value. But smooth. Can you think of? You should be able to do it. Give me a function that look similar to that.
X squared.
Huh?
X squared.
I'm sorry?
Is it X squared?
X squared, correct. The parabola. There. Very similar. But this one, at zero, it's differentiable. Because it's smooth there. Smooth there. This one is not smooth there. It's 0. Okay. So keep that in mind. Okay. Then, it begs a question. Okay. How can a function be undifferentiable? Okay, there are 3 things for you to recognize. Okay, let me put it down. 3 possibilities. Okay. That leads to undifferentiable. First, f of x has more like a sharp turn or a corner at A, which is what we just saw. Maybe this. There. That number A is not differentiable. Okay. So undifferentiable. And remember, differentiability usually everywhere, we learn that, everywhere or at one point. This function, undifferentiable exactly at this point only. Right here, if I pick another point right there, okay, it's still good. You can still take derivative. You can still find limit. You can find limit. You can find limit. Everywhere, over here, good. But right there, specifically right there, A, you cannot take derivative. Okay. Another option, okay, we talk about this discontinuity. Clearly, discontinuity at A. Discontinuity. Okay, there are very easy way to draw that, right? I'm going to give you some example. Okay, jump down here, maybe, yeah. There. A, B, yeah, clearly. At A and at B, discontinue. Because discontinue, rather than T, undifferentiable. Okay, third. When f of x go to infinity, go to right here, negative infinity, positive infinity. Okay, generally, how do we say it? Asymptote. F of x has, to be precisely, vertical asymptotes. And even stronger, vertical, we are talking about derivative, right? Vertical tangent. Okay, look at this point. Let's pick that point. The tangent line right there, literally straight up or straight down. Okay. And a point that have vertical tangent line, you can find the limit. Yeah, mathematically, if you have a vertical tangent line, I don't want to bring up a too complicated example, but mathematically, that point, if we give you a function that has a point like that, draw a vertical tangent line, you cannot find the derivative right there. Okay. Do the math, do the different quotient. That edge, you will never able to cancel that edge. In other words, that limit. Okay. Okay, vertical tangent line or vertical asymptotes. Okay. And because we say vertical tangent line, so it doesn't have to be look like this. It doesn't have to be always look like this. One example, yes, vertical tangent line, vertical asymptote, there, shoot to positive infinity. Definitely not differentiable at A, but another scenario like this. There. There. This function. First of all, this function clearly, you can see clearly, go to positive infinity. So at A, not differentiable. Right here, this function, continuous. It's still continuous. Very smooth too. Very smooth too. But right there. At a point somewhere in here. Somewhere in here. There's a point that you're able to draw a vertical tangent line. That point will not be differentiable. Okay. There. Because if you draw there. Okay. Therefore, we have a very important theory, very important theorem. If a function f of x is differentiable then f of x is continuous. Actually, differentiable at A, at a number, then continuous at that number. If a function is differentiable at a number, at a point, then that function is continuous. Guarantee. Then I ask you this question. Can you say backward? It's true. Okay. First of all, I want somebody to say this sentence, that statement in backward. Not backward like A at continuous E. No. Backward in terms of meaning. Okay. So if I say something is differentiable, that guaranteed to be continuous. Okay. A function is differentiable. You can take the derivative of that function. Guarantee that function is continuous. Then what would be the backward of that?
If a function is continuous at A and it is different, f of x is differentiable.
At A. Yes, that's the correct statement. That is correct way of saying backward. If a function is continuous at A, then it's also differentiable at A. Is that true or false? In other words, okay, I'm going to summarize. Differentiable is continuous. That's true. That is this theorem. That's it. That's simple. Differentiable and continuous. But continuous, does it guarantee that function is differentiable? Yes or no?
No, right? Because
I just show you. Yes, correct. No. Yes. Right here. Look at that red one. Continuous. Is it differentiable right there? One of the three scenarios. Right here. Continuous, right? Differentiable or not? No. So keep that important theory in mind here. Okay. Not everything you can say backward. This is the first thing. Okay, we're gonna encounter this kind of theorem a few more times throughout this class. Okay, a few more times. You say in one direction, that's true, but the other direction will not be. The statement will not hold. Okay. All right. Next thing, higher derivative. Higher derivative. Okay, this one relatively simple. Okay, relatively simple because if you're able to take the first derivative, you should be able to take second and third derivative. Okay. What does it mean by second derivative? You take the derivative twice. Okay, take derivative twice. That's it. Or another way of, plain English, in plain English. Derivative of derivative. Okay, you take the derivative, whatever you have, you take the derivative of that one again, then you have the second derivative. Okay, and this holds true for all kind of order derivative. Third, fourth, fifth. Okay. Okay, notation wise, what does it look like? How do you write a second derivative? Okay. Right here, let me show you this. Derivative is this, right? That is a derivative, right? That's a derivative. Then derivative of derivative is that, right? Derivative of derivative, and you can write that in short like this. So second derivative, usually they say this is f double prime. If you use the prime notation, double prime. Or y double prime. Or second derivative of y, right? Double prime. Prime, that means first derivative. Another prime, second derivative. Okay. How about Leibniz notation? Leibniz notation, the one with the d. So you want to take the, okay. First derivative, it look like this. df over dx is look like that. You want to do another derivative there. Okay. First derivative, second derivative. Okay, derivative of derivative, derivative delta, right? A bunch of them connected by the letter d. Difference, right? Derivative of derivative. But usually we write in short like this: d squared f over dx squared. Okay. It's actually true in here. Look at it. Look, note it. Okay. Treat everything in here, every letter as a number. Treat every letter as a number. You see that dx times dx squared, right? You see that letter d times d? Yeah, actually true. Okay. There. Depend on how, if you were writing in terms of f or in terms of y, they're basically the same. Okay. So that's second derivative. Okay, so may as well gonna give you a third derivative, just extra, right? Third derivative. So f triple prime or d cube of f over dx cube. Same for the y notation. Okay, and so on. Okay. Okay. So take the second derivative and third derivative of that function. I will do the, okay. Actually, in order to get the second, you need the first, right? You cannot bypass that. You need to have the first derivative. AKA f prime of x. And, okay, some of you familiar with the derivative formula, and then somehow you write like this. And second derivative, you're going to have this. And the third derivative, you're going to have this. Each answer is correct. But if this problem is 10 points, you get 3 points. Right? Do you understand why? That is correct. This is also correct. This is also correct. But if this problem is 10 points, you get 3 points. Why is that? Huh?
No proof.
What?
There's no proof.
No proof? Yes. We are not doing formula yet. Into next section, to be right after this section, the next section, you will be able to do that in one step. But now, at every arrow, look at that, every arrow like that, a lot of things happen. What happened there? So let's try that. Okay. Calculus is learn what happened in here. Not apply this yet. What happened in the middle? That single step in the middle, that invisible step in the middle. A lot of things happens. Okay. Okay, so try that. And this will be yes without saying. This kind of question is going to show up on your quiz tomorrow, right? Right. That we've been talking about this like how many times already? Like 50 times already, right? I've been writing this limit, this definition like 50 times, right? We've been writing this like 50 times already. So I cannot stress enough that you're going to show up tomorrow on your quiz. You're going to show up on Friday for sure. You should be able to do the limit definition of derivative. And yes, feel free to use the derivative formula to verify your answer. Verify your answer. This is how you write out to verify your answer. But to show your answer, you should be able to do that. Or Q. If you look closely, or if you recall, last week we did this example right there. Last week we did the first derivative already. What was it? Down here. We did that. I just recycled the problems. So 3x squared minus 1. Okay. So but however, if you don't know how to go from there to here, make sure able to do that. 3x squared minus 1. Okay. Look above, right? 2 pages before. Okay, now second derivative f double prime. Okay, second derivative f double prime of x okay. What should I write up here? I mean, in terms of formula, in terms of the notation. Should I write this? Should I write that? Second derivative is derivative of derivative, right? Derivative of derivative. So you take derivative, this one, you take derivative of this one, right? So inside this formula, which function you're using? If you write it as f of x, you're going to write the one above there, right? The original one. Nope. You are using the derivative. To take derivative one more time, you're using this one. So you're using the prime one. There. So this one is the one going to go down here. Okay, try that. And yes, the answer should give you 6x. Okay. Right. That's how you fill in the formula. Simplify. Do you? Everybody got 6x? 6x. Right. Anybody have different answer? 6x. Okay. When you have that, one more time. Third derivative. Third derivative. Now 6x. Much easier now. You should have 6. Much easier now. But this should be 6x. Negative plus 1. Yeah, you can cross it out. You don't have to. Do you have access to Canvas?
No.
But I did email you on the note, right?
I sent you an email. It says I need like you to give permission for anything.
Yeah, I did. No, but before that, I gave you the email with on the handout, right?
Oh yeah, I got all those.
No, make sure you print that out. Sure.
Okay, thank you.
Good. Hold on. You should go. Oh, this one. Expand this one. Don't distribute it. It does not x. Okay, x squared plus x squared is not equal x squared plus x squared. Each one of them. Okay, expand this one. There are 3 terms in here. If you expand that, there are 3 terms in that. Okay. Very important to know that this is not equal x squared plus x squared. In fact, it should be like that. Okay, you're gonna see that a lot. Okay, you're gonna see that a lot. Make sure you get that properties. Negative 1 plus 1 cancel. Right? Keep simplifying. You get 6 for the last one. Okay, you should get 6 for the last one. Okay, if you have 6x correct. Now one more time. Now third derivative. Practice now. Third derivative. If you have the second, then do it one more time. The last one should be extremely quick. Do it another time to get on the way to 6. Okay. Technically, this one go first. Okay. Right. Go. 1 cancel 1. Okay. I'm gonna return your quiz tomorrow, and most of the group, not really most of the group, a few of the group don't get full credit because of this. Like I said, because of just this. That. Remember that, right? This is not equal that. I very, no, I don't want, yeah, strict with writing math. In our department, I'm the strictest one in the writing math because I learned from also very strict professor about writing math. Equal means a lot. When you say equal, left and right has to be equal. They are not equal. Now they equal. Okay.
If I were to be plugging things in, do I need to put that in front?
Correct question. Question. Good question. If you put the plug in, now you can drop it. If you plug in, but you still keep it, then now that is going to be incorrect. That would be incorrect because you already used your plugin already. Okay, keep that in mind. 6x. Okay, I will not go too much detail. I'm just going to give it to you. If you follow the limit definition, you have 6. Okay. Not done. You need another page in here. However, this is also equally important. Learning about derivative is just not learning about this definition alone. That definition, very important, yes. But learning derivatives also learn about the function behave, the graph of that function. So I have f of x is x cubed minus x. I have the first derivative, 3x squared minus 1. I have the third derivative, the second derivative, 6x. And finally, I have the third derivative, it's just number 6. Your answer in terms of equation has to be consistent with how you plot these one. So I will plot the first one, the original function, that one, x cubed minus x. That's just a cubic function. It will look like this. That is f of x. Okay. 0 right here. X squared. Positive 1 and negative 1 there. Okay. That will be f of x. Don't look at this one. Use this as to compare. You should be able to look at this curve and draw the derivative of this one by one. You can draw on top of this. Okay, let's try that. Recall last week, look for the place where you have the horizontal tangent line, right? That will be the zeros of your derivative. Okay, try that. But when you feel, actually we did draw this. Actually, yeah, my bad. We actually draw that, right? Right here. Okay, yeah, right there. Nice. Just last week. Derivatives of that. Okay, I'm going to draw that on top. Then draw the next one. Okay, if I draw this, you draw the next one. So on top of this will be the derivative of that. There. This is f prime of x. Okay, Now try it yourself. What would be the second derivative? 6x. And then after that, the third derivative. Are they consistent? You can draw on top, you can draw on another x, y axis. Okay. And later, this point right there, it means something. Later, you're gonna see that they has the name, critical points. Critical points. A point where you have a horizontal tangent line, or the slope is 0, flat, slope is 0. Slope is derivative, right there. That purple one is the derivative. The derivative, 0 right there, right? 0 right there. So the derivative is 0. When the derivative is 0, you have critical points. Okay. Then, when you have second derivative equals 0, you have inflection points. Technically, this point right here, 0. Okay, 6x. Why is that? Is it consistent? Okay, let's analyze it. This black one, okay, because we were already used the blue one, I'm gonna erase that. So make you less confused. There. This black one, it is. We had this because of this, right? Not this, right? We use the limit definition formula applied to this. We get this. Okay, we get this. So this and this are the relation between them. We don't relate this one to that one. Okay, so therefore the black one come from that purple one, right? And notice, right here, is about the behavior, right? Before, on the left of 0, on the left of this y-axis, on the left of y-axis, it goes down, right? Clearly, go down, go down, go down, go down. Look at the slope. Rarely slope down. Slope down. But what happened to that slope? It's negative number, right? But it keep, what happened to that? Increase, right? Increase. It's negative number. It's negative number. Increase to 0, right? Look at this black one. It's negative number down here, but as we go to the here, it keep increasing, and on the way to 0. Okay, and after this y-axis, okay, following this y-axis, the slope right here at this moment is 0. Okay, if I go follow that purple one, the slope increase, very big slope. Yeah, right. 0 increase. Right. Make sense? Then what do you think? If you don't have this, you have that, is that cheating? Right, that's simple. If you don't have that, you just have that black line, okay? Now, what would be my derivative look like?
Just 6?
Huh?
Just 6?
Just 6. Wait, but, okay, 6 is a number in terms of geometry. Look like, what does it look like?
Oh, it's horizontal line is y equals 6.
Yes, horizontal line, because it keeps increasing. Look at this one. increasing from left to right. Don't worry about number 0 in the middle. Just look at that line. It increasing steadily, continuously at a rate 6. That's why you have that. Okay. You see how derivative connection, right? Graph by graph is explained carefully. And that's one thing about math too. The function, you apply those limit things, those formula, even those doesn't have any relation to the plot. This one completely separate from this plotting. Just use the limit definition. You get to this, that cubic. This is a parabola. This is a parabola, shift down by 1 unit. This is a line 6x. That is a horizontal line. Okay, using derivative, you get each one of them. You get using the limit, you get each one of them. But somehow when you draw them, they also match perfectly. Okay. Don't you find that interesting? No? Or did I lose you? No. Okay. All right. Close out 2.2. 2.3. We're going to be able to use derivative. Okay. Everybody is saying to yourself, I can't wait to get the hell out of the limit. Okay. Okay. Get away from the limit. Okay. But still haunting you for a couple more days. Okay. So, all right. Before we move on.